Hi, my name is Pabu. Did you know that we live at the bottom of an invisible ocean of air? I will explain using the 16-ounce can. At sea level, that ocean pushes against us at 14.7 psi or 1 atmosphere. We don't feel it because our internal pressure pushes back equally. But today, we're going to use thermodynamics to prove exactly how much force is hidden in the room around us. Using these thermodynamic tables, we can see that for 100 degrees C, the specific volume is this for liquid water, and the specific volume for water vapor is this. So here, we can find the volume ratio to be 1,604. Now, I will put 2 tablespoons of water into the can and let it boil. As we add heat, the water reaches its boiling point, as shown in the graph as state 1. Here, it begins to absorb the latent heat of vaporization. This is the energy required to break molecular bonds and transform liquid into vapor. For water, it's a massive 2,257 kilojoules per kilogram. By boiling a small amount of water, we are manipulating a specific volume. Calculated earlier at 1 atmosphere, the specific volume of saturated vapor is about 1,600 times larger than that of the liquid. This massive expansion purges the atmospheric air, filling our 16-ounce control volume with high-energy water vapor.
Now it's time for the grand finale. When the can hits the ice bath, we create a seal and trigger a rapid quench. The steam instantly condenses to the state 2, and because the volume shrinks by 1,600 times in a sealed container, it creates a vacuum. Now that we saw a cool phase change, let's get to the math. To find the internal pressure, we start by deriving the Clapeyron equation. We start by assuming the liquid volume is negligible due to the vapor being much larger than the liquid and assuming the vapor behaves as an ideal gas at these low pressures. Assuming the latent heat of vaporization, or HFG, and the specific gas constant remain constant over this temperature range, we can pull them out of the integral. By integrating from T1 373.15 K to T2 278.15 K, we find that the internal pressure P2 drops to 1.15 kilopascals. That is 1.1% of atmospheric pressure. Finally, we will calculate the crushing force. By integrating the pressure difference of 14.696 psi over the can's 58.6 square inches of surface area, we prove the atmosphere is striking this cylinder with 851.6 pounds of force. That is about equal to the weight of a grizzly bear. One more time.
Thanks for watching.